Thank you for coming. I guess many of you came for the beatboxing, right? Yeah, let's talk about xeus-cpp before. So before we get to it, a few words about ourselves. So I'm Johan Mabille, Technical Director at Quantstack. I've been working there since a decade now. I've been active in the Jupyter ecosystem, where now I have a seat at the steering council, and Anutosh here with me joined Quantstack 2 years ago, mostly working on the XeU stack, and is now officially LLVM maintainer. Before we demo things, I found it important to give some historic and context, because XeU is not a new thing. It has been here for a decade, but there has been a lot of new things in XeU during the past years. So when you wanted to write Jupyter kernels, before 2017, you had only two options. So the first one was you write your kernel from scratch. It has a lot of drawbacks. So you have to learn all the Jupyter kernel protocol. You have to read Rocket manuals like ZMQ. You have to find a cryptography library to sign your messages. So it's a lot of work. Another approach, which was simpler, was to use what they call the kernel wrapper approach, which was basically inheriting from some IPyKernel class. The issue with that one is that you would depend on the Python runtime at runtime. And another problem is that you may want to expose your kernel API to the language itself for most advanced stuff like you would do in the widgets. So in 2017, we released xeus. So xeus is a library, it's a modern implementation of the Jupyter kernel protocol in C++. It's not a kernel, it's a library which is supposed to make it easier to write a kernel. So after xeus, we have a lot of xeus-based kernels. So one for Python that we used as an alternative to IPyKernel to experiments, and it made us write a debugger for the Jupyter ecosystem. We had a kernel for SQL, SQL-Lite, and the first C++ kernel was actually xeus-cling. So it was based on Cling, a C++ interpreter developed at the CERN, because the CERN believes that C++ should be interpreted and not compiled. So we had a lot of kernels. Then a new actor came into the ecosystem. It was Wasm, and so we had to split xeus. So the reason is xeus was using a middleware called ZeroMQ. I talked about that with socket, and that does not make sense in Wasm. So we split the library. So xeus was just implementation with no middleware. We had xeus-ZMQ based on xeus, and just like providing the ZMQ middleware, sorry. And xeus-Lite, which is a new Emscripten-based middleware for xeus. And that allowed us to start to port the existing kernels to the Wasm ecosystem. And when we considered porting xeus-cling to the Wasm, we faced many problems. So first problem was the limitations of Cling. So it was based on an outdated version of Clang. It has been fixed now, but at the time we had to compile with a really old version. And all the stack had to be compiled with the same version and the same standard library. So that excluded all the new standards. So you could not execute C++ 20 or 23 with the kernels. And it was super hard to maintain on all the platforms. So we had to just stop supporting Windows, and it was complicated. And so the idea was to write a new one, a new kernel. And during this time, Clang incorporated a lot of elements to write that would allow you to write a readable print loop natively. So you don't need any additional machinery like Cling. And we rethought the architecture of the kernel. So it was supposed to be an architecture based on plugins. We didn't make it, but we still have this idea, so we'll probably refactor it. And so the idea is you can make it more extensible, so you could use and execute some Python code inside the C++ kernel. So you can write some C++, some Python bindings, and just run them. You can install a lot of magics, but not all of them, because you may not want to depend on all this whole ecosystem if you just need a raw kernel. So yeah, it will be more flexible. And now let's go for demo. So the initial contract was xeus-cpp. Oh, sorry. xeus-cpp should be able to execute exactly the same code as xeus-cling. So this is a notebook from 2017 when we firstly demoed xeus xeus-cling, and it just like works exactly the same way. So we can include some stream and output stuff on cout, on cerror. We can throw and handle some exception. We can print some value. So the only thing that is still not working is the printing the last variable. It will be available with the next release of Clang next year. And of course, we have all the classical C++ features, so functions, classes, polymorphism, and virtual dispatch. So I won't get into the detail, but yeah, just show it works. So also template and template specialization work. We also support the documentation system. So it's based on tag files that you install, and then it just like redirect you to the documentation. Oh, it just told me that. That's just for, I don't know if I can extend it. Yeah, so it would just like allow you to browse the documentation directly on CPP reference. So it's not a mimic. The link works. We also have rich rendering mechanism with MIME bundle. So it works exactly the same way it would work on the previous kernel. On other kernels, we just call a display method, and it will go inside the kernel protocol machinery to send back information to the front end and display it. And you can override what you want to display. Then you have audio example. Works too. It's not bitbox. I'm a bit disappointed. You also have the update display. So the idea is that you can update something that's already displayed on the front end. Don't know. Yeah. We have some mechanism to clear and reset output. So here some output and just clean. Oh, I think there's more bug here. And you can also ask for input to the user. And yes, hopefully it works. So yeah, we are like almost feature parity with the old xeus-cling. And now I will just give it to Anutosh so he can show the WASM kernel.
Okay, thank you, Johan. So now that you all know what xeus-cpp Lite is, I shall be speaking on xeus-cpp Lite. xeus-cpp Lite is xeus-cpp plus jupyter-lite. Hopefully, most of y'all attended the talk yesterday on the mscript-info stack and jupyter-lite. If some of y'all missed that, I'm going to give you all a quick overview. So jupyter-lite is a JupyterLab distribution in your browser. It is being powered by WebAssembly. So it demands you all to have a WASM build for your kernels and the required packages that you might be interested in. And preferably, these should be hosted somewhere. This is where mscript-info is coming in. Mscript-info is mscript plus conda-forge. It basically helps us to build and package stuff for the WebAssembly platform. It's a GitHub repo. We all can contribute to it. It has some growing set of recipes, all targeted towards mscript and WASM 32. Now, my question here is, what would it take to come up with xeus-cpp Lite? We obviously need to compile the entire stack, LLVM, cpp interop Zeus, and finally our kernel xeus-cpp for WebAssembly. So there's a lot of cross-compilation going on here, throwing stuff against mscript and getting a WASM build and hosting stuff on mscript and forge. But taking 2 steps back, think about it. We are not just trying to run some pre-compiled static C++ code here. We are trying to have a REPL, a live interpreter in the browser, and this has its own set of challenges. So we need to talk about some runtime execution here. Clang REPL on native platforms is making use of LLVM's org-JIT. Now, how this JIT works is it will convert your source code into machine instructions at the fly, place them in memory, jump to that memory address, and execute it. Classic just-in-time compilation. But in the browser, WebAssembly enforces a strict sandbox model. So we can't just write executable instructions in the memory at runtime. So there's no traditional JIT in WASM as of now. And yeah, we had to tackle this next. How we did that is we introduced a WASM backend for Clang REPL during LLVM 17's development cycle. So Clang REPL already had a very well-established incremental executor based on top of LLVM's orgjit, as I told you all. But we had to come up with a WASM incremental executor here for WASM-specific executions. So this involves around 3 to 4 steps. I'll quickly educate you all on what those are. So let's say you have some code in cell X or input line X. Now this gives you a PTU or a partial translation unit, which is then lowered to some LLVM IR, and it's compiled to give you an object file. Now this object file is fed to WASM LD, and with some appropriate flags, you have a standalone WASM module. These WASM modules act as dynamically linked side modules, which are meant to be loaded on top of your persistent main module. And that main module comes out of your kernel. We call it xepp.wasm. So every cell X generates an incremental wasm module, which is then loaded on top of xepp.wasm. And how this works is using mscripton's DL-open mechanism. So one might just think as to how these modules are communicating back with each other. So there's shared memory going on, and there's symbol resolution going on at runtime. So the incoming cells have access to all the definitions taken place in the previously loaded WASM modules. So this gives us a concrete proof of concept that we can run Clang REPL in the browser, and sort of motivates us to host LLVM and xeus-cpp on mscripton Forge. And we end up with a configuration like this. Now, it's kind of important to highlight this configuration here because mscripton as such prefers static builds, but y'all can also see some shared objects here. We realize that switching back and forth between static and shared builds can significantly affect compile time and execution time for cells in xeus-cpp Lite. So yeah, this discussion spanned over quite some months, and this is probably the best design we ended up with. I think that's all the theory I had. So yeah, now we'll jump into some demo. Being a static link, you all could try it out on your phones too. So I'll say the first thing we wanted to achieve here was at least cover what the native kernel could do so that we could establish xeus-cpp Lite as a working WASM kernel. So we just started with some basic C++. You have your output and error streams, some exception handling. This is the same notebook that Johan demonstrated. You have functions, some classes going on, inheritance, and some polymorphism. You can do templates too. Then you have some inline documentation. You can utilize the !magic command to perform a lookup and yeah, just fetch some documentation from CPP reference. Something like this. Probably open the discussions forum here. You have some image and audio examples. So we are integrating C++ in the Jupyter ecosystem. We can leverage Jupyter's rich rendering capabilities. xeus-cpp can't just output plain text. We can do images, audios, HTML tables, LaTeX, and even custom visualizations. So here's a Marie Curie image for you all. How this works is through the xepp display function. It sends a MIME bundle to the front end. Let's play some drums. Yeah, here you go. The same display, we can update those displays, and yeah, we can also play around with clearing the outputs, something like this. So this technically tells us that we are in a good state to at least cover what the native kernels were able to do, and this sort of motivated us to explore more. So we tried building on Jupyter's rich rendering capabilities and integrating it with a framework like SDL. Mscripton comes built in with some really good SDL support. We just need to build our main module with the use SDL flag for some advanced graphics. And how we did that is we are showcasing Kevin Beeson's small PT example here. So it's global illumination in 99 lines of C++. I think there's a loop going on here, and if you run the loop for around 10.3 hours, you get a clear image. I'll just run it for around 10 seconds. It'll be a okay image. So I think how this works is it's the width, height, and the number of samples that dictate the time it should run for. This should run for around 10, 15 seconds. So how this works is the illumination is being rendered by SDL onto an in-memory canvas, which is then being captured and displayed using the xepp display function. So yeah, it should look something like this. Next, we move on to some scientific computing, which involves symbolic and numerical computation. You all might have heard about the Python libraries, SymPy and NumPy. SymPy is symbolic Python, NumPy is numerical Python. Wouldn't it be great to have their C++ counterparts also working with xeus-cpp-lite? And we tried exactly that. So I started with SymEngine here. SymEngine is a fast C++ symbolic math library, allowing us to do all kinds of math, from calculus to some algebraic manipulation. It's based on top of Boost, so we have Boost here. Here's a Boost product for you all. We can define some SymEngine expressions, display them, and also expand them. It should look something like this. Next, we have some array-based computation. So as you all know, Jupyter is pretty famous among researchers, students, and scientists for array-based computation. And one such framework that helps us do so in C++ is Extensor. So Extensor is a C++ multidimensional library with a NumPy-like syntax, enabling us to do all the numerical computation from array broadcasting to element-wise operations and much more. We can extend Extensor to have Extensor BLAS. Extensor BLAS makes use of the high-level syntax Extensor has to offer and the performance of OpenBLAS, which means you can make NumPy-like convenient BLAS and LAPACK routine calls through it. So for Extensor BLAS to run, you obviously need OpenBLAS loaded. Here's a LU decomposition algorithm for you all. You have your factorized matrix. We can now sort of fetch some documentation for Extensor and copy paste some examples. I think the example below, is it this? Yeah, it's the same example from the getting started page. So you have some arrays, you have some views. You can reshape those arrays. Next, you have your Extensor BLAS-based examples. Yeah, and you can do, you can compute matrix ranks, do some matrix inversions, and compute eigenvalues through this. Give me a second. This works. I'll show you later. So next, we have some SIMD acceleration. We can try out some raw WebAssembly intrinsics first. So WebAssembly comes built in with a 128-bit SIMD instruction set that is being powered through the wasm SIMD 128.h header file coming from Clang's resource directory. So yeah, here's an addition operation for you all. This is okay, but we can make it look better. Writing specialized vectorized operations like this in WebAssembly can get cumbersome. And this is where a framework like xmd comes in. So xmd is a C++ library providing a high-level SIMD API that abstracts platform-specific vectorization instructions. So I'm going to run the same example, but with a much better syntax here. OK, I think I need to reload this notebook. Give me a second. Yeah, I think so.
It's working now. Oh, it's okay. Are you good? That's the full windowing.
Wait, I don't see anything on my screen.
Refresh. Well, refresh.
It's here. Yeah, so all the demos again, I think. Yeah, you have the extensor blast-based examples working now, and I'm just going to show you all the SIMD demo through XMD now. Yeah, and we have the expected result, but with a much better syntax. So now we can move to some interactive widgets beyond Jupyter's rich rendering capabilities and some inline documentation. We can also make use of Jupyter's widget ecosystem and have some interactive components going on in our notebook. And one such framework that helps us do so is xWidgets. So xWidgets is the C++ implementation of the Jupyter widget protocol, and yeah, provides us with all the core widgets, and also serves as the foundation for libraries like xleaflet and xcanvas. So you can have some buttons, you can have some sliders, you can have some canvases, play around with them, something like this. You can have canvases. And lately, Thorsten worked on a concept called an off-screen canvas, which helps you respect your mouse events. That should look something like this. I think this is really cool. Next, we have some magic commands. So magic commands aren't part of the programming language. They are just special commands that assist the user with code execution. So we have file magics to start with, which should help you create, read, and write to a file. So I'll just show it here. We should have a tmp.txt with all these statements, and yeah, we can fetch those contents too. Next, we have the Mamba install magic. I think this is my favorite one out of all of them. So we should be able to fetch any package that is hopefully hosted on Emscripten-Forge, and just use it at runtime. I'm fetching doc-test here and defining a simple test case that is bound to fail. Hopefully it fails. Yeah, it fails. We are good. Next we have the time it magic. So we have a working prototype for this, but our solution here is hacky, and we are trying to improve it. So yeah, the time it magic should help you clock or benchmark the execution time per cell. It should look something like this. Next, we have something like loading third-party or custom libs. So let's say you have some C++ source code and some custom functions like I've shown you all. You all can have it compiled to get a WebAssembly shared object, something like this. And then you should be able to load it in the file system in jupyter-lite, and using Emscripten's DLOpen, you all should be able to use your custom functions at runtime inside xeus-cpp-lite. Yeah, this brings me to the end of my demo, but here we have some near future work here. Now I term this as near future because all of this is being done right now. All of these involve contributing to LLVM, and most of these are API and ABI breaking changes. So these patches organically land maybe when LLVM 22 is out, during the end of the year, I think. So first we have last value printing. This is something xeus-cling supported. We are trying to port it to xeus-cpp. So you can just omit the semicolon and still have an output, probably trying to replicate a Python shell-like syntax. It should look something like this. I think this is really cool. Next, we have debugger support. So my Google Summer of Code mentee, Abhinav Kumar, has been working under me on this. We should be able to debug C++ in a REPL format now. Let me quickly show this. So we have 4 cells here. We define 4 cells. If you click on the debugger button, you have a debug panel for you all. You can set some breakpoints, inspect the source for that breakpoints, inspect the variables there, and have a call stack for your. You can step in, step out, continue, and execute the next function here. So this is basically making use of LLDB and LLDB DAP, which is also present upstream, and it's making use of Jupyter's debug protocol. So yeah, this should be available in the upcoming versions of xeus-cpp. Next, we have CUDA support. So you should be able to use CUDA in a REPL format. CUDA is Compute Unified Device Architecture and is used for parallel processing. So you can define a CUDA kernel, allocate some data, and have some results like this. My PR implementing support for this went in just 3 weeks back, so it should be picked up soon. Next, we have some Python interop here. So we should be able to support a Python magic using the X plugins framework. Yeah, so you should be able to define a C++ function and then call it from Python-like syntax, something like this. So yeah, that's some Python interop for you. And finally, we have something like multiple interpreters. So the concept here is you should be able to have sub-interpreters defined within a single kernel. So yeah, this is a C++ 17 kernel. But as you all can see, we have a sub-interpreter defined here with different optimizations and different C++ versions. I think we are calculating the elapsed time here for a cell. So yeah, you all can see it here. And we can also create another sub-interpreter within the same kernel using a different C++ version and maybe a different optimization level. And yeah, also have the elapsed time calculated here. And once you define the sub-interpreter, you should just be able to make use of it, something like this. So yeah, I would also like to thank the compiler research group from Princeton that has, and Google Summer of Code that has funded a good chunk of this work. And yeah, that brings me to the end of my talk. I guess we can have some questions now.
Thank you so much, Anutosh and Johan. Fantastic talk and really like a new paradigm of programming with C++ on Jupyter. Let's have some questions.
Thank you. I was wondering, the CUDA support is for Xeus or xeus-cling also with WebGL?
We've just tried the native kernel now. I'm not sure about xeus-cling. I need to look into it.
Okay. Thanks.
Okay.
More questions?
Yes, one quick question. When you are doing iterative development, are you able to rewrite a modified version of a function?
I think so. Yeah, that should.
Not yet. So it will be available in the next version of Clang. But yes, it's something that you can do. You could do with xeus-cling, and you will be able to do with xeus-cpp.
I could not do it with Cling, so that's
okay.
why I'm asking.
So that's a bug. It should have been fixed actually. So okay. But yeah, it should be available in the next version, and if not, it's a bug that you can report, and we will fix it. Okay. So it should be. Yeah, we should do that.
It is now. Okay. Okay.
Okay. Any more questions?
This isn't directly related, but I think everybody at my company loves xsimd. Is there a xGPU or something coming
I think
soon?
Johan is the guy to answer. He wrote xmd.
Well, we can talk at.
All right. More questions? We have some time. 2 minutes, 2-3 minutes.
Oh, yes, here.
Oh, okay.
More comment than a question, but since 2017, we've been using xeus-cling with hundreds of students at the university, and I'm super excited. Thank you.
Thank you.
Always. For me, I would just have one question because I'm pretty much floored by like this integration of C++ with Jupyter. Familiar with Jupyter, beginner in C++. So just know that C++ is known for its speed. Do you think this integration could affect the speed of execution of C++ programs?
Yeah, well, you have to compile it before you run the function. So yeah, of course, you have some additional time and performance hits on top of it. But it's more for exploring and for educational purpose. It's not for running code in production.
Exactly. That actually you answered my second question. That is, who is the target audience or target user for this?
So education and prototyping.
Okay, great. Okay, if you have any more questions about this, oh, great.
So about displaying data, can I like add callbacks to define the displaying of another library that I did not implement myself, or does it have to be done inside the library?
No, you can overload some function where you just like define how you would like the data to be rendered. So.
All right. If we don't have any more questions, a big round of applause for Johan and Anutosh.